Hello and welcome to our today's talk about future-proofing your applications with API regions and OSGi. Who are we and what do we do? Well, we're David Bosschaert, working as a senior software engineer for Adobe, remotely from Ireland. He's been working with OSGi specifications, or on OSGi specifications, I should say, since a long time. And he's a member and committer at Apache. And I'm Karl. I also work for Adobe, remotely from Berlin. I'm a long-time Apache member as well. And I'm mostly working on Apache Felix and Apache Sling. And I've been working with OSGi pretty much since the beginning, in early 2000s. So today we want to talk a little bit about some of the work we've been doing at Adobe in the past year or so in the area of building and maintaining an OSGi platform over time. And towards that end, we're going to introduce a novel concept called API regions, and we will show you what they are and how they work, as well as you can design them, and then ultimately how they are enforced at runtime and checked during build time. So if we, at the beginning here, zoom out a little bit, then really the topic is related how you can build a platform over time. And the first thing you need is an API. I mean, that's true for most systems, obviously. But when it comes to platforms, it's a little bit more important, maybe even that you have a good way to manage your API, because that's pretty much all the users of your system have to do all their tasks. They cannot do anything outside of or out of band. They have to go through your API for everything. So it's very important that you can expose an API, but also that you can maintain it and evolve it over time. So likewise, since typically your platform is about to grow and to become more complicated, you need some kind of internal API that your own building blocks are using to work together. That typically should be hidden from the outside, or ideally completely, but nevertheless, it needs to be there and evolvable and maintainable as well. And then over time, you typically run into the problem that you get some gray areas in the API parts too. You have to make some maybe backwards and compatible changes. You want to deprecate some parts. Mistakes do happen. So if you have something that's around for a long time, it becomes all sorts of shades of gray. And then ultimately, you might even have a real use case for optional parts of APIs or optional APIs, because let's say you have customers that you want to license certain things out, especially to like extensions or add-ons, right? So you get all those kind of levels of API in your platform over time. And the question is, how can you deal with that? And so just to re-emphasize the use cases here, so we get some API, that's our platform, and it's the divider between the worlds, and we have an implementation that provides some value to consumers via that API, right? So that's the use case that is fine and that we want to enforce. And then in the second step, we have some internal implementations that communicate together via the internal API. So that's fine. But what should not happen is that you get a situation where that leaks, quote unquote, to the consumer directly or is used by the consumer directly. So that needs to be prevented, because this part would not go through the API. However, as I said, there can be cases where that is exactly what you want, that you effectively have two channels available to the consumer. And so we want to support that as well by being able to provide additional API, which is not part of the normal API, but nevertheless is something we can add to the system to make that communication be okay. So in that case, we then have two APIs, and the implementations provide the values for the different ones. how can we make that possible? Well, we're talking in our case Java here, and Java has as a, well, historically at least, the concept to do anything in that area was a class loader, right? So class loader can be used to provide some isolation between application parts. And Java-EE, for example, used that mostly for doing similar things. So you would load your WAR file into a class loader, and it would only make part of the outside world available to you while the implementation stays hidden. Nowadays, you have the Java module system, which provides some more advanced things, but obviously in AEM, we have those since a long time because we use OSGi. So in OSGi, we have a couple of powerful building blocks that can be used for doing what I just described with APIs. First and foremost, the unit of deployment, the bundle, already is isolated, so everything inside the bundle is private to that bundle, with the exception of things you explicitly share out as export packages, right? So that's a nice start for exposing API. Then in the second place, we can version those packages, so you can add version constraints on top of them, and that is nice because you can this way signify changes to your API and even breaking changes if you follow the semantic version convention, where you say if I increase a major version, then this is a breaking change. That can help. And then ultimately, there's some more constraints you can put on packages in OSGi, but I'm just going to go into them right now in too much detail. And then last but not least, what makes OSGi nice in these areas is that you can have multiple versions of a given package active at the same time. So that's called side-by-side versioning. For example, it's possible to have two versions of the same package available, so that if one part of your application uses this version and the other one uses the other one, they can still coexist, at least in most cases. But that's pretty powerful stuff, and AEM is using that since a long time. And I think AEM really is a testament of what you can do with those building blocks and how far you can push them. Because it's pretty amazing. I mean, if you look at it, we have hundreds of bundles, thousands of packages, tens of thousands of services all running in the same process. Some of this code is, more than 10 years old. Some has been written just today. So, and all of this works like it does. It's pretty amazing and shows the power of those concepts. However, when we switch from the on-prem to more of the cloud service world, we get a little bit of a change here, because what used to be conventions and documentations and best practices that people followed and paid the price directly if they didn't, because their own system wouldn't build anymore, right? It's now a little bit more divided because we get that code and it has to run, but we are running the system. So avoiding problematic cases in such a setup becomes harder. And maybe even backwards compatibility becomes a bigger concern. So we wanted something to enforce these things at runtime, and also to help us check it at build time better. And so OSGi provides something in that area already. It's called OSGi subsystems, which is a way where you can hide away parts of your application and selectively share things in and out of these so-called subsystems. And we explored that. I think David Bosschaert even had a talk about it at adaptTo a couple of years back. But for various reasons, we ended up not taking that, in parts because it mandates some changes to your application to make it usable, and we didn't want to or couldn't do it in AEM. And we opted to create something ourselves. It's called API Regions, and it's hopefully more lightweight and geared more towards a declarative approach, working together with the feature model. And David Bosschaert now is going to tell you all about it.
All right. Thanks, Karl. So yes, API Regions is designed for this from the ground up, and it can solve all these problems. And so let's look at how it's working and how it does that. So first of all, it does this by also working on the package level, just like the exported packages in OSGi. So let's say this pyramid here is, or this triangle here is your platform. And on the left-hand side of the triangle, there are the user bundles. The user bundles should get as much freedom as possible, should not be hindered by your platform's internals. On the right-hand side, there are the platform parts, the private platform parts, and at the top is the platform API. So in terms of API regions, we call this the global region. The global region is visible to everybody, the platform as well as the user. Now, for the rest, things that are not in the public API of the platform, you would like to hide that as much as possible from your users. So let's look at it how this can be done with API regions. So let's start at the bottom. Now, individual bundles, as Karl already mentioned, they can hide packages from other bundles by simply not exporting them. So that's standard OSGi functionality that's already there. And if you can use it, you should use it. Then if their bundles provide packages or API that are to be used by other bundles, they can declare this API through the export package header in the bundle. Now, in the context of API regions, this has a little bit of an extra meaning in that the exported package by default is only visible within the feature that this bundle resides in. So if your platform is built up from multiple feature models, which I think is always a good idea to modularize your platform with different feature models, then by default, the exported packages from a bundle are only visible within the one feature that the bundle exists in. Now, obviously, there are also APIs that you want to make available across your platform, but not necessarily to your users. Now, for example, a logging API. You want to have the same logger throughout your platform, but maybe your user wants to have a logger too, and they happen to pick the same one that you chose as an implementation detail. They shouldn't be stopped from doing that. And more interestingly, they might have different configuration for this logger, so you really want to keep them apart. So this is possible by creating an internal region, and this internal region basically is visible only to your platform, to all the features in that platform and all the bundles in those features, but not to your users. So it allows you to have the same package twice, both internally in your platform as well as in the user area. Okay, so how do you define these API regions? They are defined as extensions in feature models. So here are two example feature model snippets. The left one, you can see that this feature model exports a package called org.myapi into the global region. And it also exports another package called myutil into the myinternal region. And by exporting into these regions, it also kind of joins them. So it can also see the packages that others export into these regions. Now, the global region is kind of special because everybody can see that region without having to explicitly, join it. So that one is special. The one on the right-hand side only exports an API into the global region, which means that this feature model, even though it might be part of your platform, actually cannot see the internal region because it doesn't opt into that region. So if you want to have a feature model that sees that region, so for example, the green feature model here, you can basically just state that it joins the myinternal region. It doesn't have to export anything into it. And that green feature model can actually now see both the global region, because that's the default one, everybody can see it, as well as the internal region because it opts into it. Now, in terms of usability of the API regions for the users of your platform. Now, generally, API regions are the concern of the platform designer. Users really don't need to know about them at all, typically, and stuff just works for them. So it's a really simple for users. It just works, and actually it works better than without API regions because interference is basically excluded, right? It stops interfering implementation details from your platform into implementation details from your users by keeping these things separate. All right, and then designing the regions for your platform. So the region that needs most care in the design is the global region because everybody can see it. Because it's your API, it would always be best to keep it as small as possible, at least in my opinion. Small API is easier to understand, but it also means you have to maintain less in the future to your customers or to your users, which means you don't, you have more opportunity for refactoring. So a small global region is always good. As regards to your internal region for your platform, and you can have multiple of those even, that's up to the platform designer. You can make them lean or you can make them rich. I would personally still make them lean, but if you change anything there, or if you make them rich, your backwards compatibility concern really is only towards yourself. So it's really up to you how you design that one. And as I said, these internal regions, they don't affect any users. So you don't have an external backwards compatibility issue there. As Karl already said, the API regions are verified. They're verified both at build time as well as at runtime. The build time validation works through taking the feature models that are involved in your application. So there's a feature model for your platform, but also feature models for the application that the users develop themselves. You feed all these feature models through a Maven build into the Sling Feature Maven plugin, and that one passes the features on to analyzers. Now, there are a whole lot of feature model analyzers, but there is a number of them specifically aimed at API regions. And they can do a variety of things. For example, they can check whether your feature is not using any API regions that it's not supposed to use, right? So you can define these in such a way that they exclude, that they disallow end users from using your internal region. And if they do, that you will get an error during the build. They will check that there's no duplicates, because normally you should only put a certain API in a single API region, not in more than one. It checks whether the APIs you mention in your API regions actually exist are provided by the bundles, which is good for keeping these two different definitions in sync. And last but certainly not least, they check whether the required packages, basically the imports, are visible to the importing bundle, and we're taking the API regions into account, effectively checking whether the API regions will allow to provide all the packages that are needed by all the bundles. So once the build is finished and everything's good, you can publish your feature models in a Maven repository or store them somewhere else, or just launch them if you want for further use. And then there's also runtime enforcement. This is, for cases where people somehow bypass the build time enforcement. Build time enforcement is always, static analysis is always better because you know upfront that stuff is going to work or not. But the runtime enforcement also gives you early warning. Now, first, let me show you how package resolution works in OSGi. When there's a bundle that needs a package from another bundle, the OSGi resolver gets involved and tries to find a bundle that can provide the package the other bundle needs. And if it has found it, it will basically wire these bundles together. Now, for the API regions, we have a runtime bundle, which is actually an OSGi bundle fragment. And that runtime fragment registers an OSGi service called the Resolver Hook Factory, which is a standard OSGi service that influences how the OSGi resolver works. And it can basically check the API region's definition to see whether this bundle A is actually allowed to see bundle B. And if not, it can influence the resolver to make it stop resolving bundle A to bundle B. And the nice thing about it is that the runtime overhead, all of this is happening during the resolution phase. So once all your bundles are resolved, the API region's runtime is not involved anymore. There's absolutely no runtime penalty for it after the resolve phase. And during the resolve phase, you won't notice it anyway. It's really, really, really fast. Okay, and then finally, I just wanted to kind of note briefly just some tools if you are debugging. Because debugging is sometimes necessary with these things, and a lot of people use the web console. The web console is not API regions aware. So in this example here, I have a bundle that I created. I called it AEM Private Importer. I installed it into AEM, and it imports a package comdaycqx widget, which is not part of the public API. It is somewhere available in the bundles in AEM because it's an internal package, but it's not available to users. So if you press the play button here on the right-hand side, it will not resolve, even though the web console thinks that it should, because it gives you the provider. So in a situation like this, what you really need to do the troubleshooting is you have to look at the log. And in the log, you will see a warning where the resolver hook service gets involved and basically tells you that this bundle is trying to resolve to an internal package or to a package that's in the wrong region, and it basically prevents it from doing that. It'll tell you the regions that the bundle that the requirer has and that the provider has, so it'll tell you exactly what it's doing, and it'll tell you why it removed this candidate. And then what you will see is that there's an error showing up typically if the bundle cannot be provided by another package. And then there's a little tool here. You can look up the Resolver Hook Factory service itself in the service registry, which will then show you the definitions files that it uses to act on the API region. So if it doesn't behave the way you think it should, you can look at these resources to see the definitions that it's acting on. And with that, I'd like to give it back to Karl for a little demo.
Thank you. Right, so now that we know what it is all about, let's try to briefly look at how it works with a little toy example here. Pretty much following what David already said. I noticed there was one question in the chat bot, just so we don't forget about that one. But yeah, I mean the web console, it should be possible to make it API regions aware eventually, but it just didn't happen yet, right? So it's one of the limitations we still have to work on. So let's look at a little example here. It pretty much follows what David said and what I showed at the beginning of the slides. We have a couple of projects. We have an API bundle. We have two internal implementations, Impl and Impl2, and we have a consumer project here. And then the idea is that we will tie the implementation and the API together into a platform, and then subsequently use that platform to tie it together with the consumer in an image, and then can start and run that image. Okay, so the API, it's pretty simple for now. It just really has two packages, Demo API and Demo API v2, and we created a feature for it, which is in this API JSON here, and it defines some API regions in the JSON. So as David already showed you, we have the global region, and we export the Demo API v2 package into that global region, and we keep the Demo API around in the deprecated region for people that opt into it. So remember, global is available for everyone. Deprecated would mean that they would need to opt in. And we've seen an example for that in the Impl. The implementation feature actually does do this here, where it says name deprecated in the API regions. That makes it opt into the deprecated region, so it can see the Demo API, and it also publishes an internal API package, the Demo Impl package. And that is then used by the Impl2, which for that reason has to also opt into the internal region, and it does here, where it says, okay, I'm opting into the internal region. So now that we have all of that in the platform, and the platform itself just sets up a very simple feature here, where it only puts the API hooks David mentioned as a bundle, the API regions bundle, and the configuration to make them work. But other than that, it just aggregates together using the Sling Feature Maven plugin our platform, so the Demo API feature and the Impl and the Impl2 together into a new feature called Core. And then it submits that feature to the analyzers to say, okay, verify that our exports and imports work. So when that is done, we have a new platform core feature, which is our platform. And as I said, we're going to try to combine that with the consumer together in an image. And the image really is just, again, an aggregation of that core platform feature together with the consumer. And then again, we run yet another set of a round of verifiers over it to again make sure that it works. So if we build all of that, it hopefully will work right here. And we get a working system out of it because we don't detect any problems with it. And that is what happens. So now we can go into the image and actually start it. I prepared a little bit of a run command here. It's just taking the API region extension on the class path and the feature launcher to launch our features that I showed here, together with web console feature that we can actually see something. So when that is running, we end up with a working web console here, and then we can actually look at our demo bundles. They're all here, they're all active, everything worked. So now what happens if I actually do something to evolve my API, and let's, for example, say I want to get rid of my deprecated region here. I can do that, and then we will see what happens. So that is just us saying, okay, we don't have a deprecated API anymore here. Now, if I come back and build my system, it should hopefully eventually catch that. And it does. It will catch it in the platform part where we check for our internal consistency. And it tells us exactly that, yeah, I mean, the demo impl is trying to import the demo API, but that is not available. Okay, so that one, at least for our internal consistency, we could catch. Now let's look at the consumer and say, okay, let's have the consumer be actually using an implementation, which it shouldn't. And first of all, the first level of defense here is that it can't because it doesn't have the classes. But now that's good. So we should always only develop against the API jar, right? But if let's say he can find the implementation jar someplace so that the consumer actually will build and end up in our image, then we hopefully will catch that violation already at build time when we build the image. And we do, and this time it's not the platform failing, it's the image failing. So it tells us that didn't work. Now, and to conclude the demo, as David mentioned, if we now go in and let's assume this sneaked through and we actually still start the system, even so our build time checks that fail, then we end up in this situation where we in the logs get that catched at runtime, where it complains about it and tells us that it couldn't resolve it of this reason. So consequently, the web console will show us that the demo consumer did not resolve. It stays in the installed state. So is there a way to make such a scenario then still work for the optional API part? Yes, you could. That's again due to OSGi. We could actually make it so that the consumer itself provides the implementation. And that would then be fine because it becomes part of the consumer. And we want to allow that, right? So he basically provides its own implementation of the features they need. So we add that to the consumer feature, so it becomes part of the consumer, and then hopefully everything should work, and it does, at least on the build time checks. And so, yeah, with that, I think we're pretty much running out of time, and that's the demo.
Great, thanks, Karl. There are a few questions. There's this one here that you already answered around the web console, whether it can be made API regions aware. Sure, that is absolutely possible. There are the web console is completely pluggable, so that is absolutely something that can be done. There is this one here. Let me see how I do this. Live answer. How do the regions handle dependency change when the package can be obtained through two dependency paths? So I guess I can try to answer this, and Karl, chime in, please. So let's say if there are two bundles providing that package, and one of them is in the platform internal region and the other one is not, the way it works is the OSGi resolver gets two candidates for resolution. And the API regions might just remove one of them because it's part of the internal platform, but the other one is still available. So then the resolver will pick the one that is still left as a candidate. So yeah, it's then one of them might win if it's publicly available.
Right, but then it follows the OSGi conventions at that level. Yeah. Right. Let me jump the queue here because there's one interesting one by Konrad, I think. Does it show up now?
You have to click.
Yeah.
Yes, there it is.
Have you considered using the already existing directives X friends and X intern from Micronox? I mean, that's interesting. I hinted at that one, at least in parts, because you can do something similar, at least with package constraints. But well, first of all, we're not running on Equinox, so that'd be tricky. And we really wanted to have a way to do it outside of the whole metadata of the bundles themselves and do it inside the feature model. Maybe I was too quick in the demo, but I mean, the main idea is that you can change all of that declaratively in the feature model to be flexible in how the system works.
Right, and there's another one here. Can feature models and API regions concept be used in AEM to support multi-tenancy? I would say no. API regions are not a security concept. And I think it has been proven already numerous times that multi-tenancy within the same JVM is not a good idea. So I would say no. All right, I think that's all the questions done.
And we are out of time.
We're out of time.
Yep. We're already 2 minutes.
Thanks everyone for the attention.
Yep. Thanks.
Bye-bye.
Bye.